Suppose you're a researcher in genetics, and suppose you sequenced a gene and got the sequence of bases A, B, A. Usually, the four bases are denoted by G, C, A, and T. But in this video, for simplicity, we're going to call them A, B, C, and D, and we're going to call them letters instead of bases. So you got this A, B, A sequence. You're wondering what's the probability that you sequence this gene and get A, B, A. Your friend Ellie, a fellow biologist, gives you this table and tells you, see, it's obviously 1 over 124. You start blinking in your puzzlement, but you're not the kind of person who gives up easily, so you decide to go on an adventure in order to figure out this probability stuff. So, what's probability? You ask your friend Margot, so she explains. Suppose you sequence only one letter, the first one in the gene. It could be A, B, C, or D, and it cannot be anything else. But you know, for example, that all genes start with B, so you're absolutely certain that the letter is going to be B. To represent this certainty graphically, you could take a stick, paint it all blue, and then close your eyes and point to a random point on that stick. That point is just as likely to be near the center of the stick as it is likely to be in any of its ends, because you blindly choose the point and have no clue where you pointed at. If you pointed at a blue point, congratulations! The letter that corresponds to the color blue is B, so the first sequenced letter was indeed B. So now, let's figure out a way to numerically represent this 100% certainty. Suppose the length of the stick is 1. Then the red length is 0, the blue length is 1, the green length is 0, and the orange length is also 0. So according to the color-to-letter correspondence, we can say that the probability of sequencing the letter B was 1, and the probability of sequencing the letters A, C, and D was 0. This was not very interesting, was it? Let's sequence one more letter. For the second position, we know that sequencing A and sequencing C are equally likely, and sequencing B and D is impossible. We paint half of the stick red for A and half of the stick green for C. Now, if we close our eyes and randomly choose a point on the stick, we are as likely to choose a red point as we are to choose a green one. Well, suppose the chosen point was green. Then, respectively, the sequenced letter must be C. Now, let's try to represent these 50-50 chances numerically. We know that the length of the stick is 1, so 1/2 of this length is red, and the other 1/2 is green. Looking at the color-to-letter correspondence, we can say that the probability of sequencing A was 1/2, B was 0, C was 1/2, and D was 0. Let's place these numbers below the second position. It's time for the next example, the third position. Here, we know that all four letters are equally likely to be sequenced. We can represent this graphically by coloring the stick in all four colors, where each color covers the same length as any other color. To sequence the letter, let's close our eyes and pick a random point on the stick. It happened to be a red point, hence the sequenced letter was A. Now let's try to represent numerically that the chances were the same for all letters. We know that the length of the stick is 1, so 1/4 of this length is red, 1/4 is blue, 1/4 is green, and 1/4 is orange. So, looking at the color-to-letter correspondence, we can say that the probability of sequencing A was 1/4, B was 1/4, C was 1/4, and D was 1/4. Let's place these numbers below the third position. What we got is a table of numbers. The same kind of table from which Ellie made her conclusion earlier. Let's interpret this table. The first column contains information about the probabilities in the first position in the gene. Here, only B has a probability of being sequenced. In fact, it has the highest possible probability, 1, the length of the entire stick. Hence, all genes that are described by this table must start with the letter B. The second column contains information about the probabilities in the second position in the gene. Here, only A and C have a probability of being sequenced. In fact, they have equal probability, 1/2 each. B and D are impossible to appear in the second position. That's why we painted half of the stick in A's color and the other half in C's color. Hence, if we sequence many genes that are described by this table, about half of them will have A in the second position and about half will have C there. The third column contains information about the probabilities in the third position in the gene. Here, all 4 letters have a probability of being sequenced. In fact, they all have equal probability, 1/4 each. That's why we painted the stick in all 4 colors, using the same amount of paint for each color. Hence, if we sequence many genes that are described by this table, about a quarter of them will have A in the third position, about a quarter will have B there, and the same goes for C and D, a quarter for each. So now that we have an idea of what probability is, we want to finally understand what was the probability of sequencing ABA for the first 3 positions of our gene. The probabilities for the first 3 positions are given in the table. For each position, the probability that the sequenced letter is A is given in the first row, the probability that it is B is given in the second row, that it is C is given in the third, and that it is D in the fourth. Remember that Ellie quickly came to the conclusion that the probability of sequencing ABA was 1/124. What she meant is that it is as likely to sequence ABA from this gene as it is likely to randomly pick a green point on a unit length stick, which is only 1/124 green in length. But this is not at all obvious from the table. When you ask her how she got this number, she explains. At the first position, we sequenced A, and the probability of A is 1/2. For the second position, we sequenced B, and the probability for that to happen is only 1/31. For the third position, we again sequenced A, where the probability of doing this is 1/2. So, 1/2 times 1/31 times 1/2 equals 1/124. This explanation may sound reasonable, but it still feels quite unsatisfying. Why do we multiply these probabilities? This is the product rule, Ellie says. Ah, I'm a free spirit. I don't like rules. Let's see if we can discover the truth about this 1/124 probability ourselves, without trusting any authority other than logic. We know that each column can be represented as a painted stick. So let's transform the table into its visual representation. Now, let's focus our attention on the first 2 positions only. We're going to look at the third position later. For now, let's ask ourselves, what were the chances that we sequenced AB? In other words, what were the chances that our hand pointed at a red point on the first stick and on a blue point on the second stick? Let's rotate the second stick and create this angle shape. Let's ask 2 people to close their eyes and point at a random point on the sticks. Notice that their choices can be represented by a single point, the intersection of these 2 dashed lines. Each intersection point can lie anywhere inside the square defined by the 2 sticks, and each point inside of that square uniquely corresponds to one point on the left stick and one point on the top stick. So instead of asking two people to point at the two sticks, we could have asked a single person to point somewhere inside the square at random. Now ask yourself, which points in that square would correspond to sequencing AB? Well, this region definitely corresponds to sequencing A for the first position, because the left hand must point at a red point on its stick if the intersection point came from the red region. Similarly, this region definitely corresponds to sequencing B for the second position, because the top hand must point at a blue point on its stick if the intersection point came from the blue region. The intersection point that you see on the screen corresponds to sequencing CC. Now it corresponds to sequencing AC. And now it corresponds to sequencing AB. So it is exactly in the intersection of the red and blue rectangle, that purple rectangle, where the intersection points should be if we want it to correspond to sequencing AB. So, out of all the points in the area of the square, we want to see what the chances are of the chosen point to lie in the area of the purple rectangle. Well, since the square's area is 1, we can just compute the area of the purple rectangle, and this will be our probability. The height is 1/2, given by the probability of sequencing A in the first position, and the width is 1/31, given by the probability of sequencing B in the second position. So the area is 1/2 times 1/31 equals 1/62. And this is the probability of sequencing AB in the first two positions. This corresponds to the area of the purple rectangle with respect to the area of the whole square. So, if we were to represent this probability of 1/62 on a stick, we would want to collapse the square of area 1 into a stick of length 1, and then paint 1/62 of that stick in purple. Hence, it is as likely to sequence AB from the gene for the first two positions as it is likely to randomly pick a purple point on that stick, which is only 1/62 purple in length. If we were to color the rest of the stick in some color, say yellow, then this color would correspond to sequencing any pair of letters in the first two positions that are not AB. This could be BC, BA, AD, CD, or anything else, as long as it is not AB. So we color the rest of the stick in yellow. Now we remember about the third position in the gene, where we sequenced A, and sequencing A in this position is associated with the probability of 1/2. In other words, the red length on that stick is 1/2. Now we are interested in the probability that we sequenced ABA for the first three positions. For this to happen, we must have sequenced AB for the first two positions, which means that the top hand points at the purple segment. And we also must have sequenced A for the third position, which means that the left hand points at the red segment. Hence, the intersection point must lie in this green rectangle inside the large square. It corresponds to sequencing ABA. To find its area, we multiply its length 1/2 times its width 1/62, and that's it. 1/124 is the probability of sequencing ABA, because 1/124 is the area of the green rectangle, and out of all points in the area of the square, only those in the area of the green rectangle correspond to sequencing ABA. The rest correspond to sequencing some other letters. Finally, to represent this probability on a stick, we collapse the square of area 1 into a stick of length 1, and then paint 1/124 of that stick green. So this is what Ellie was thinking when she took the numbers 1/2, 1 over 31, and 1/2 and multiplied them to get 1 over 124.